My name is Lotfollah Najjar. I'm a second author, professor at University of Nebraska, Omaha College of Information Science Technology. And Samira, the first author, she was my master student, but she got a job now. It's a private company. And the third author is Parisa Darabi from Texas at University, Dallas at University of Texas. The topic is optic disc or OD and optic cup or OC, segmentation using UNet and its variant for improved glaucoma diagnosis. This study basically evaluated deep learning models for automatic segmentation of the optic disc, OD, and optic cup, OC, in retinal images, which is important for glaucoma detection through the cup to disc ratio. Or CDR. For segmentation architecture, UNet, UNet++, LinkNet, Feature, Pyramid Network, and DeepLab V3 Plus were tested using two different backbones. One is ResNet's 50 efficient net B7. And actually this is supposed to be 5 segmentation. Sorry. And glaucoma compromises a group of ocular disorder characterized by progressive damage to the optic nerve, often leading to irreversible vision loss. And everybody might be familiar with that. Of course, early detection in any medical cases is essential and effective for monitoring and treatment, and it plays a critical role in preserving visual function through deep learning. Fundus imaging is a key diagnostic tool in this context, providing high-resolution photograph of the interior surface of the eye, including retina, optic disc, and macula. These images, they are awesome, enable detailed visualization of the optic nerve head, which is crucial for the diagnostic and progression monitoring of glaucoma. According to the most recent analysis, glaucoma is the second leading cause of blindness following cataract. And of course, most of you or all of you know about it. Epidemiological studies estimate that approximately 79.6 million individuals were affected by glaucoma in 2020. And a number was forecasted to be 111.8 millions. It is estimated that up to 90% of glaucoma-related blindness could be prevented through timely detection and proper management. To achieve this, of course, early screening is always essential and typically involve one or more of the following diagnostic techniques. intraocular pressure measurement, visual field testing, and assessment of the optic nerve head. Now, motivation. Glaucoma is the leading cause of irreversible blindness. As I said before, a manual segmentation of the optic discs and optic cup is time-consuming and prone to observer variability, or basically error. What is the goal? Develop an automated, accurate segmentation system using deep learning to calculate cup to disc ratio, or CDR, a key metric for glaucoma diagnostic. So in this study, widely used deep learning model for image segmentation, namely UNET 1, UNET++ 2, featured Pyramid Network 3, LinkNet 4, and Deep Lab V3 5 were employed for segmentation over 2 backbones. What is UNET architecture? Is convolutional neural network architecture specifically designed for biomedical image segmentation task. That was introduced by Ronberger and featured symmetric encoder-decoder structure. The encoder captures context through successive convolution and max pooling layer, while the decoder enables precise localization via upsampling operation and skip a connection that concatenate feature from encoder to corresponding decoder layers. Now the other one, the second one, UNET++ architecture, is an enhanced version of the original UNET architecture that introduced a nested and dense skip connection designed to improve segmentation performance. That was proposed by Zhou. UNET++ aimed to reduce the semantic gap between encoder and decoder feature maps by using series of convolutional block along the skip pathways. This redesign results in more accurate segmentation, especially for complex biomedical images. The architecture also supports model pruning and assemble during inference to further improve efficiency and robustness. The third one, feature pyramid network of FBN architecture, is a multi-scale feature extraction architecture originally developed for object detection but widely adopted to dense prediction tasks such as semantic and instant segmentation. So FBN enhances the representational power convolution neural network by constructing a top-down pathway with lateral connection, enabling the model to generate high-level semantic feature maps at multiple scales. This hierarchical design, as you see in the figure, allow effective detection and segmentation of object or region at different sizes, which is especially valuable in medical image analysis. The fourth one, link net architecture, proposed by Charo Rizisa Claricilla is a lightweight and efficient semantic segmentation architecture designed to achieve fast interface while maintaining high accuracy. It employs an encoder-decoder structure in which each decoder block is directly linked to its corresponding encoder block via residual connection. So this type of links allow the decoder to efficiently reuse special information from the encoder, leading to reduced computational complexity and improve segmentation performance, particularly in real-time and resource constrained environment, when we do have some limitation and constraint regarding the resources. The fifth one, Deep Lab V3 Plus architecture, introduced by Chen, combine an encoder-decoder framework with address dilated, separated convolutions. Of course, the encoder captures multi-scale contextual information using address spatial pyramid pooling ASPP, while the decoder refined the segmentation result by recovering object boundary with high spatial resolution. By leveraging both global contextual information and fine spatial detail, Deep Lab V3 Plus achieves superior segmentation performance, and we are going to see it in the final result across a variety of datasets, including challenging biomedical image tasks. So that is very promising. So the evaluation matrix is, one is intersection over the union, or IOU, is widely adopted for evaluating segmentation performance. It quantifies the overlap between the predicted segmentation and group, truly measuring the ratio of the intersection to the union of the predicted actual region. Mathematically, it is defined as TP divided by TP plus FP plus FN, where TP represents true positive, FP false positive, FN false negative. That is the union, that intersection of this, among this. A higher IOU indicate better agreement between the predicted and actual masks. So that is one of the measurements that we use. The other one is dice similarity coefficient, DSC, which was performed much better among the other of the backbone. Is another metric used to evaluate the similarity between two samples, how similar they are. It is particularly sensitive to class imbalance and is often preferred in medical image segmentation. Dissimilarity coefficient, mathematically defined as 2TP divided by 2p. The difference between these two is only this multiplied by 2 and this also multiplied by 2. So they are the same. This is how they are going to be measured. The result, the quantitative segmentation result for UNet, UNet++, FPN, LinkNet, and Deep Lab V3 plus model using ResNet 50, these are one of the backbone, and efficient net B7, that is another backbone. Backbone are summarized in table 1, and you're gonna see it here. These are the two backbone. Each has DSC, and DSC, which is dye similarity coefficient, and we already talked about that, is intersection over union. They both have these two features. And you will see the measurements are kind of different. For example, if you see DSC for all the 5 features performing very well. That is the evaluation performance scale of 100% or 1, 0 to 1. And actually, Deep Lab V3 Plus, you will see, is across all of them except IOU of this backbone is a little low, but is also performing better compared to the rest. So the quantity segmentation result of all this using in table 1, the corresponding training and validation. Also, we have done training and validation to make sure our result is sound and robust, is over 100 epochs are depicted to see at what point, what number of epochs out of 100 they will converge, or the loss stay the same. And these are in figure 6 and 8 corresponding to ResNet 50 and efficient B7 respectively. Quantitative segmentation output are presented in figure 7 and 9. So these are basically the quantity of segmentation result for all of them, are the 5 approaches over 2 different backbone, ResNet 50, efficient net 50, which they have the same things, 2 feature here, 2 feature there, and these are the degree of performance evaluation. Except UNet++ is a kind of weak here, that is bold. Actually is the highest among the rest, but still is not close to 0.90. But you will see DLC is all the 5 approaches over DLC for efficient net are very high, especially for Deep Lab V3 Plus, because that is performing excellent compared to the rest. So across both backbone, DLC value remain consistently high over 0.90. That is DLC. These are above 0.90. There is no 0.80 at all there. So the DSC is performing very well, especially regarding Deep Lab V3 Plus. Among the ResNet 50 based architecture, Deep Lab V3 Plus achieved the highest. That is the Deep Lab. Both regarding IOU is the highest, and also regarding DSC. While the efficient B7 backbone overall performance improved with DeepLab V3 Plus again, achieving the highest DSC 0.9556, while UNet++ attained the highest IOU, slightly suppressing DeepLab V3 Plus 0.8319. And anyway, all the results are clearly shown here. UNet and LinkNet exhibited nearly identical score. Basically, they are very close to each other. With the efficient NetB7 backbone, overall performance improved, with DeepLab V3 again achieving the highest DSC, which is 0.9056, while UNet Plus attained 0.8348, slightly suppressing there. The difference among the top performing model were minimal, within plus minus 0.003 margin of error, DSC, indicating that this dataset is well suited to multiple encoder-decoder configuration. The consistent advantage of DeepLab V3 Plus, which is the last one, across both backbone, underscored the importance of multi-scale feature aggregation for optimal optic disk and optimal COP segmentation performance. And you will see it here. Figure 6, training and validation loss for various models with ResNet 50 backbones. Figure 7, segmentation result for various models with ResNet 50 backbone. Training and validation and segmentation result. And you will see that at almost at epoch of 40, it got flat out. The loss is going to stay the same, but the loss is going to decrease, but at almost 40, is flat out, plateau. That is training and validation loss for various models with ResNet 50 backbone, one of the backbone. And these are the segmentation results for various models with ResNet 50 backbone, which is more clear. That is training and validation loss for various models with efficient net B7 backbone, which is this one. So we did this and now this one. And you will see that it's almost the same for training and validation. Conclusion. This study compared 5 advanced deep learning models, UNet, UNet++, LinkNet, FPN, DeepLab V3+, for optic disk and optic COP segmentation 2 backbone in retinal fundus images using Harvard Fair segmentation dataset. The models were evaluated with ResNet 50 and efficient net B7 backbone using dye similarity coefficient DSC and intersection over union metric. The results showed that the DeepLab V3 Plus consistently delivered the best segmentation performance, outperforming the other architecture across both backbone configuration and, as we saw right here. Except for IOU, basically, which is kind of, they were all low, but still this one is the, okay. I hope you enjoy it. And is about deep learning, is a kind of from AI and machine learning. And she did a good job doing all this analysis. And thank you so much for listening, and bye.